Probability distribution is exactly what it sounds like. When we talk about a probability distribution, it's some type of tool that lets us know how probability is distributed amongst the possible values. Okay, the values of what would be a random variable. A random variable is a numerical or quantitative variable that assumes random outcomes. That's probably not the best way to say it, but for instance, we've talked about an example where we look at the number of boys or girls born to a family of 3 children. Okay, that's a random variable. The fact that the child is a boy or a girl is not a random variable, but when we start to count something about that process, then that's what we call the random variable. So it has to be quantitative, and the outcome that it takes on is, randomly assigned. We don't say, well, before technology and all that stuff, we don't say how many children there will be, how many boys or girls there will be in 3 children. The probability distribution could be a chart, it could be a graph. We're going to see that it could be a formula that basically assigns probability to different outcomes. Okay, and it's calculated, not just some random assignment. But when we talk about a probability distribution, there will be 2 things that you want to do. First of all, we're going to list all possible outcomes. And then list the probability associated with each outcome. All right, so keep that in mind. We're starting here at the beginning of the chapter to talk about probability distributions in general. And then we'll talk about one in particular. There are lots of different probability distributions, but at the end of the day, when we construct a probability distribution, we have to do these 2 things. List all the possible outcomes and the probabilities associated with each one. Okay, so I think we have an example. It says, consider the offspring of peas from parents both having the green-yellow combination of pod genes. Under these conditions, the probability that the offspring has a green pod is 0.75. That is, probability of green is 0.75. If 5 such offspring are obtained, and if we let x equal the number of peas with green pods, okay, right here we define that random variable, okay. X is going to be the number of peas with green pods among the 5 offspring. They want us to construct the probability distribution. Okay, so we could do that. First of all, we're going to list the possible outcomes. What are the possible outcomes for green-yellow pods? Well, actually, it's the number of green pods among 5 pods. How many could be green? 5 could be green. Is there any other possibility? 4, 3, 2, 1, 0. It's possible for 0. So these are all of the possible outcomes. Okay, 0 through 5. Then, to finish this, we would need to calculate the probability of getting each of these. Okay, and 5 and 0 we could do pretty easily. Okay, they already told us the probability of getting a green is 0.75. That means the probability of getting yellow is what? 0.25. And if we're talking about yellow and yellow and yellow and yellow and yellow, that would be 0.25 to the fifth, right? Okay, whatever that comes out to be. And then on the bottom, if we get all green, that would be what? 0.75 to the fifth. Okay, we could figure out what that is. The others are a little more complicated because we got to think about which one is going to be green. Is it the first one or the second one or the third one? Or here, which two are going to be green? And so we'll talk about some formulas a little bit later that will help us calculate that. But to complete this, what we would need to do is somehow come up with all of the probabilities for each of the possible outcomes. That's what a probability distribution does. Okay? Questions about that? All right. Come on. All right. Let's see. Is there a special note concerning very small probability values? I'm not sure. I don't know. Maybe that'll come to me later. I can't think of what that's supposed to be. Okay. All right. So there are two types of random variables: discrete and continuous. We've talked about discrete and continuous random variables already. With the discrete random variable, what types of things do we look at? Things that we can do what to? Count. Okay. Variables that count. Okay, they only take on certain values, not all possible values. There are gaps between the values that they can take on. So, for instance, the number of green pods is discrete. Versus continuous, we said those are things that we generally do what to? Variables that measure. Okay, and they can take on any value within a certain range. Okay, so we talk about height and age. Well, depending on how you measure age, but height. Let's say the time it takes you to complete a task, temperature. Those things are continuous. Okay, in this chapter, we are going to focus on mostly discrete random variables. Okay. In the next chapter, chapter 6, we'll focus on the continuous random variables. They have some similar characteristics, but there'll be things that we need to do differently to handle them. Okay. All right. So just for some examples, let's look. Let's look at these examples and see if we can determine, or I think I already gave them to you. The following are examples of discrete and continuous random variables. X is the number of eggs that a hen lays in a day. X is the number of stats students present in class on a given day. Those are discrete. Okay, continuous, the amount of milk a cow produces in one day. Okay, that would be something that we measure. It could take on any value between 0 and however much the maximum value is. The measure of voltage for a particular smoke detector battery can be any value between 0 and 9. It doesn't have to be exactly 0, 1, 2, 3. It could be, 5.6798, whatever. Okay? All right, so some examples. Okay, the total amount in ounces of soft drinks that you consumed in the past year. Okay, would that be continuous or discrete? Okay, continuous. Very good. All right. B, the number of cans of soft drinks that you consumed in the past year. Okay, discrete. All right. Okay, grams of sugar in 1 serving of a soft drink. Continuous. Okay, that's weight. The running time of a randomly selected movie. I would say continuous, depending on, if your measuring instrument is sensitive enough, it doesn't have to be one, a whole minute. It could be some fraction of a minute. Okay. The cost of making a randomly selected movie. Discrete. Now this one, remember when we talked about money, it has decimal values. There's still gaps between it. Okay. Except at the gas station where they charge like what? How does it go? 299.9. I mean, it's just crazy. Okay, the number of movies currently playing in U.S. theaters. Discrete. Excellent. Okay. All right, so we know the difference between the two. Okay, a probability histogram is another one of those things that we could look at that would allow us to see how probability is distributed amongst the different outcomes. So it's a histogram showing how probability is distributed among the different outcomes. Okay, so if we've got a histogram, that means we've got 2 axes, and so on our horizontal axis, we would have the different outcomes. So it could be the number of children or the number of green pea pods or whatever. And then on the vertical axis, we're going to have the probabilities. Okay, and we'll probably look at one a little bit later. Okay, now here's something else. This has to do with the requirements for, I should probably add the word for a valid probability distribution. Okay, I already told you earlier, in order for us to have a probability distribution, it lists all the possible outcomes and the probabilities associated with each one. But in order for that to be valid, we have 2 requirements. First thing is the probabilities, I'll write it just briefly, is 0 has to be less than or equal to p of x less than or equal to 1 for each value. Okay? Every value in the probability has to be between 0 and 1. All right? And the last requirement is that the sum of all of the probabilities has to be equal to 1. When we add them all up, when we add up all of our probabilities, we get, excuse me, a total of 1. Excuse me. Okay, so determine whether or not a probability distribution is given. Caffeine Nation. In the accompanying table, the random variable x represents the number of cups or cans of caffeinated beverages consumed by Americans each day. Okay, so do we say yes, this is a probability distribution, or no, it's not? Okay, yes. All right. We can see here that each of the probabilities is between 0 and 1, and I heard your calculators going. Sounds like you added them up, and they add up to 1. Okay. So yes, this is a probability distribution. Okay. For B, groups of 5 babies are randomly selected. In each group, the variable x is the number of babies with green eyes based on a study from Dr. Soni at Indiana University. The symbol 0 plus denotes a positive probability value that is very small. Okay, so when we add these up, do they add up to 1? Okay, yes, approximately. There could be some round off error, but should be approximately 1. And again, we see that each value is between 0 and 1. So this one is also a probability distribution. Okay? All right, so that's what we're looking for in order for it to be valid. All right, some other characteristics that we can talk about when it comes to a probability distribution would be the mean and the standard deviation. And so our formula for the mean of a probability distribution is the summation of x times p of x. Okay, that's how we find the mean for a probability distribution. And what this gives us is the long run average. If we repeat whatever the experiment is over and over and over and over and over again. Remember we talked about the law of large numbers in the last chapter? Okay, this gives us that long run average. After we've repeated it a large number of times, this is the mean in theory. Okay, variance is let's see. It's the summation of x squared times p of x minus mu squared. That's going to be our variance for our probability distribution. Yes. And then, of course, the standard deviation is going to be the square root of that. So sigma equals the square root of the summation of x squared times p of x minus mu squared. And of course we're going to look at how we could do this on our calculator. Okay, round-off rule for mu and sigma squared, he tells us, is we're going to use one more decimal place than the number of decimal places used for the random variable x. Okay, so if our variable goes out to one decimal place, we're going to round off to 2. Okay? All right, let's look then at this example. All right. Okay, here's the example that we did earlier, and I went on and filled in the probabilities for that particular experiment. Okay, so again, this is the one about the green pea pods. We can say that the probability of getting 0 green pods is 0.001, probability of 1 green pod, 0.015, and so forth. Okay, are these the numbers that you got for 5 and for 0? Did anybody actually do those out? When we did 0.25 to the 5th and 0.75 to the 5th? Okay, you got those numbers. Okay, very good. All right, we'll figure out a little bit later how we get the numbers in between. So if we were to do this by hand, remember that the formula for the mean is the summation of x times p of x. That means I'm going to take each x value and multiply it by its p of x value. Okay? And then the summation says do what? Add all those up. So if we're doing it by hand, we would get 0, because 0 times 0.001 is 0. We get 0.015. Okay, we get what? 2 times 0.088 is what? 0.176. Okay. 3 times 0.264 is 0.792. Thank you. 4 times 0.396. Okay, and then 5 times 0.237. 1.185. Okay, very good. And so we add all that up and we get we don't have to divide by 5. Okay. Okay, 3.752. All right, so our mean is 3.752. Okay, 3.75. Okay, so stop and let's think about what that means. Remember, the mean is still a measure of the center, right? So when we look at these probabilities, where would you say the center might be? Between what two numbers? 2 and 3, okay. We hardly have, what, 0.1 on between these parts. So we'd have 0.1 here, 0.9 there. That's a little too much. Maybe if we came down a little bit farther, okay, that kind of balances it a little more. Do you see how I'm looking at the probabilities to kind of figure out where the middle is? We got 50% roughly, you know, somewhere between these two. And that's exactly what we saw, okay? At 3.752, that's kind of the central value right in here. So it's a measure of the central value, okay? Do you see how we're still looking at the center? Okay, so that is our mean. To get the standard deviation or the variance first, we're going to actually square x and then multiply it by p of x. So we still get, for the first one, 0. For the next one, it's 1 squared times 0.015, so we still get 0.015. Then we get 4 times 0.088, and that's going to give me what? Okay, 352. Then we've got 9 times 0.264. 2.376, okay, and then we get 16 times 0.396, okay, 6.336, thank you, and then 25 times 0.237, 5.925, very good. Okay, so then we add all of those up. That gives us just this piece, and then we're going to subtract from that the mean squared. Okay, so if you add all of those up, what'd you get? Anybody? Okay, so we get 15.004 minus 3.752 squared. Okay, and we get what? Okay. All right, 0.926496. And if we take the square root of that, that would give us the standard deviation, which is 625. Okay, very good. All right, while this is on my mind, if we paid attention to our round-off rules, our x values went out to just, well, really no decimal places. So it would probably be enough for us to just stop this at 3.7 if we're worried about being consistent with probably my math lab, maybe 3.8. And then here we're going to call this 0.9 and call this one also well, actually it'd be 1 if we round it. Okay, so that's how we do that. Okay, that's a lot. All right, let me show you how we can use our calculator to get that same answer. On the calculator, what we're going to do is put this data into a list. Basically, what we're going to look at is using the procedure for a weighted mean. Okay, because that's what this is. When we look back at the data that we have here, we've got x values, and these probabilities could be considered to be what? Weights, right? So just the way that we calculated a weighted mean earlier, that's how we're going to get to the weighted mean here as well. Okay, so we'll go to Stat, Edit. In my list, I'm going to put in my x values, which I think were 0 to 5. Okay, so 0, 1, 2, 3, 4, 5. And then in another list, I'm going to put in my p of x values, okay, which we have right here. They're 0.001, 0.015, 0.088, 0.264, 0.396, and 0.237. Okay. Once we've got that all in our calculator, of course, we want to check to make sure we typed it in correctly. Then we did stat. We're going to go to one variable. We'll go over to calc. One variable stats is number one. Okay, then we tell it where the x values are and where our probabilities are. So I had L1, comma, L2. Okay. Hit enter. And we've got that 3.748, which hopefully is what we got, 3.752. Maybe we did some round off, but we came up with 3.748. Oh, I'm sorry, I'm looking at the, how's the difference there? I would go with this 3.748, okay? And then for our standard deviation, we get 0.96933, which is a little bit off from what we did by hand. So I'm not sure where we went wrong. Did everybody get these answers when you did it by hand? Yes, no, maybe? Okay. All right. Well, anyway, we'll probably never do it again by hand after today. So I would definitely go with these answers, okay? So here's my mean, 3.7, and my standard deviation is 0.969. If I wanted to get the variance, then what would I do? Square that, okay? So you could go to stat, go to vars. Number 5 is statistics. Okay, that was sigma there. And so we're going to square that to get our variance of 0.9396. Okay? Questions about that? All right. The standard deviation and variance are still a measure of the spread or the consistency of our data. Okay, so we have a little spread, but relatively consistent data set. All right, very good. Okay, find the mean and standard deviation for the number of cups or cans of caffeinated beverages assumed by Americans each day. Let's go straight to the calculator for this. So on my calculator, again, I'm going to go to stat, calc. First, I got to put the data in. So on edit, okay, in L3, I'll put in my x values. And for P of x, okay, I put my P of x values in L4. Okay? Everybody okay with that? And so to get the mean and standard deviation, I'm going to go to stat, go over to calc. I've got one variable stats. This time I'm going to say L3, comma, L4. And so I get a mean of 1.5 and a standard deviation of 0.8, we'll just say 0.86 or 87, 0.87. Okay. Does it make sense when you look at the probability distribution that the mean would be 1.5? Yes, okay, because this distribution is perfectly symmetric, right? We've got the highest values in the middle, we've got the same two values in the middle, and then we've got lower values on the end. They're the same. So it's going to come right here in the middle at 1.5. X equals 1.5. Okay, questions about that? Yes. Yes, I am. Mm-hmm. Okay. A J? Um, okay, stop. Let's see. L1, frequency list, you tell it, no, L1 is where you put your X values. And on your frequency list, that's where you put your, tell it where your P of X values are. They changed the operating system. Yeah, that's how you do it on there. Okay. Alrighty. That's weird. Okay. Moving on. Okay, identifying unusual results with the range rule of thumb. Okay, we talked about the range rule of thumb some time ago. Remember we said that the maximum value, maximum usual value, is going to be the mean plus 2 standard deviations, and the minimum usual value is the mean minus 2 standard deviations. So if this had to do with the number of cans of was it caffeine that's consumed daily, then we could figure out the typical values using this range rule of thumb. If this is the same range rule of thumb that we talked about a little while ago. Okay, the rare event rule for inferential statistics. Remember, we said that we consider an event to be unusual when it has a probability that's less than what? 0.05. Very good. Okay, so that's going to be our kind of guideline to say that something is usual or unusual when it's less than 0.05. Okay? All right, very good. Okay. What else do we have here? All right, so let's see what we have. In example 5, we found that for groups of 5 offspring generated from parents both having the green-yellow pair of genes, the mean number of P's with green pods is 3.8 and the standard deviation is 1. Use those results in the range rule of thumb to find the maximum and minimum usual values. Based on the results, determine whether it is unusual to generate 5 offspring P's and find that only one of them has a green pod. Okay, so they already gave us the mean, they gave us the standard deviation. So to get our maximum and minimum, we're going to look at mu plus or minus 2 sigma. They said mu was what? 3.8, and our standard deviation was 1. So typical values for the number of green pods when we have 5 offspring would be 3.8 minus 2, so that's 1.8, to 3.8 plus 2, which is what? 5.8, which isn't even really possible. But when we look at it in a practical sense, it's saying that it's not unusual for us to have 5 green pods. Okay, intuitively, when the percent or the probability of getting green is 0.75, would you agree that getting 5 green pods is not unusual? Okay, so that makes sense. So this would be our range from minimum to maximum typical number of pods. So based on the results, is it unusual to generate? I already answered the question. Is it unusual to generate 5 offspring P's and find that only one of them has a green pod? Is that usual or unusual? For one green pod. Unusual. It falls outside of our range. Okay, so it would be unusual. Okay, use probabilities to determine whether 1 is an unusually low number of P's with green pods when 5 offspring are generated from parents both having the green-yellow pair of genes. Okay, let's see what that's all about. Okay, in the textbook, let's go back a little bit. It says we have an unusually low number of successes it says X successes among N trials is unusually low if the probability of X or fewer successes is unlikely. Okay, so basically we would say that one success is unusual if 1 plus the probability of 0 is less than 0.05. Okay, 0.05 is our kind of criteria to say that that's unusual. So we would say 1 is unusual if everything 1 or below is less than 0.05. So when we look at the example, looking at our probabilities, let's see, did I go too far? Okay. Okay, here are the well, that's for the soda. Here we are for the pea pods. When I look at the probabilities for 1 and 0, they add up to 0.016, right? 1 or fewer. Okay, the probability for 1 or fewer is 0.016, which is less than what? 0.05. So we would say that to get one is an unusually low number of peas with green pods when 5 offsprings are generated. Okay, does that make sense? A little bit? Okay. The question again was, is 1 an unusually low number? And so what I do is I go back and I look at the probabilities. I look at the entire probabilities for 1 and 0. Okay, everything that's below 1. Okay, and so when I look at all of those that are below 1 plus 1, all of that's still less than 0.05. And so we would say, yes, it's unusual to get 1. Okay? All right, very good. Yes? Where I was writing? Okay. Right here. X successes among N trials is unusually low if the probability of X or fewer successes is unlikely. All right. I think we talked about all of that. Okay, based on information from the MRI network, some job applicants are required to have several interviews before a decision is made. The number of required interviews and the corresponding probabilities are 1 with probability 0.09, 2 probability 0.31, 3 0.37, 4, you see all the numbers there. Okay. Does the given information describe a probability distribution? Okay, what do we need to look at in order to answer that question? What's that? Okay, does it add up to 1? And of course we want to make sure each value is between 0 and 1. Okay, so do they add up to 1? 0.99. Okay, so that's close enough. Okay, assuming that there was some round-off error. So the summation of P of X is approximately 0.99. Or I guess I should say it was equal to 0.99, which is approximately 1. So we're okay with that. And each value was between 0 and 1. Okay. Part B, assuming that a probability distribution is described, find its mean and standard deviation. So what would we do with this? Use our calculator. Okay, so let's do that one more time. Okay, on the calculator, I'm going to go to Stat, Edit, and I'll just start back over here at 1. Okay. So we had values from 0 to, actually from 1 to 6. I'll just delete that. Okay, and then my probabilities are 0.09, 0.31, 0.37, 0.12, 0.05, 0.05. Okay, and so we'll do stat, calc, one variable stats. I'm going to do second L1, comma, second L2. Okay, and so X bar is 2.9, or we could say 2.88. That's our average, and or our mean. And then the standard deviation is 1.2. Okay. All right, did we answer the question? Find the mean and the standard deviation. Okay, questions about that? Okay, very good. All right, D, use the range rule of thumb to identify the range of values for usual numbers of interviews. Okay, so again, to use the range rule of thumb, we're going to look at mu plus or minus 2 sigma. Okay, mu in this case is what? What was it? 2.9. Okay, and the standard deviation was 1.2. Okay, so we'll do 2.9 minus, that's 2.4, so that looks like 0.5. Okay, and then 2.9 plus 2.4, 5.3. Is that right? Okay, 0.5 to 5.3. So, you know, you got to have some interview. Would you say that it's unusual for a person to go and have just one interview? No. Okay, because that falls within our range of usual numbers of things. Okay, and that was the next question. Is it unusual to have a decision after just one interview? Okay, well, based on this, we say no. If we go back and look at the probabilities, what was the probability for having exactly one interview? What was it? 0.09? Okay, so that's more than 0.05, right? So again, that'd be another way to say that one interview is not unusual. Okay, questions about that? Okay, excellent. All right, making great progress here. What to talk about is expected value. And expected value really is just another name for the mean. Except we tend to use the term expected value when we have games that you might play, like at the fair, or betting games, or at a casino. Anything really kind of involving money. Often instead of saying the mean, you got excited about money? You know, anything involving money, we call that really expected value. So again, it's the long run average. we tend to write E of X. That's our symbol or notation for expected value, but it is still, it's just the mean. So it's the summation of X times P of X. That was our formula for expected value, or for the mean rather, which is the same thing as expected value. The trickier part of what we're going to do here is have to come up with the probability distribution. Before we can find the mean, we need to know what the probability distribution is, and we'll use some of the information that's given to us to help us figure it out. Okay? So it says you're considering placing a bet either on the number 7 in roulette or on the pass line in the dice game of craps at the Venetian Casino in Las Vegas. Okay? It costs $5 to play roulette. The prize for winning is $180. If you bet $5 on the number 7 in roulette, the probability of losing is 37 over 38, and the probability of winning is 1 over 38. Find your expected value if you bet 5 on the number 7 in roulette. Okay, so let's deal with that first. Okay, this is part A. So before I can calculate expected value, I need to come up with my probability distribution for this particular game. What do we have to have for a probability distribution? Two things in order to construct one. Okay, very good. We list the possible values and the probabilities associated with each one. Okay, and remember that X is going to be quantitative. Okay, but when we play this game, the first thing we probably think about is we're going to do what? Either win or lose, right? You're either going to win or you're going to lose. Well, those things are not quantitative, right? So now we need to take this and convert it into something that is quantitative. Okay, let's start with lose. If we lose, what's the value of that? $5. It's out of our pocket, and in fact, it's a negative $5. Okay, that's the value of a loss. We just lost $5, and the probability of that happening is what? 37 over 38. Okay, if we win, the value is what? 180, 175, right? 175, because we paid $5 to play the game. So don't forget, from your winnings, you need to subtract what you paid to play. Okay? And so the probability of that is 1 over 38. Now that we've got that, we can come up with our expected value. And in this case, just depending, it's almost just as easy to do it by hand. Remember, it's just the summation of X times P of X. So we're talking about 175 times 1 over 38 plus negative 5 times 37 over 38. Okay, so 175 minus 5 times 37 I got negative 0.26. Okay, negative 0.26. Okay, so first of all, what does that mean? Remember I said that the mean or the expected value is the long run average. So when we play, I feel like that's these are our winnings. Does that make sense? Negative 5 times 37 over 38, that's our loss. Okay. All right, according to this, the long run average is basically each person is dropping off a quarter. All right. You just might as well count on losing that much. And then, that's the long run average. If we have a whole bunch of people play this game over and over and over, at the end of the night, we would expect to get an average of about negative 0.26. You've lost. Okay. Questions about that? All right. Well, let's see about part B. Okay. It says if you bet $5 on the pass line in the dice game of craps, the probability of losing is 251 over 495, and the probability of winning, it should say, is 244 over 495. The prize for winning is $10. Okay, find the expected value if you bet $5 on the pass line. Okay, I'm not sure what all of that means, but I think I can find the mean, or the expected value. Okay, we get x, p of x. Okay, this time our values will be what? Okay, you bet $5, so you can get negative 5. Okay, and then the prize for winning is $10, but you paid $5 to play, so it's positive 5. Okay, probability of losing 251 over 495. And the probability of winning is 244 over 495. By the way, we should note that the sum of our probabilities is 1. Okay? All right, so that this is a valid probability distribution. So our expected value is 5 times 244 over 495. Okay, minus 5 times 251 over 495. I got minus 0.07. Okay. All right, very good. Minus 0.07. Okay. So, which is better? A $5 bet on the number 7 in roulette, or a $5 bet on the pass line in the dice game? Okay, we got different opinions. That basically, yeah. I mean, in this case, it's our earnings, which is negative. So here we lost 7 cents. In the previous game, we lost 26 cents. So which one would be better to play? Individually, yes. But when we talk about long run average, okay, and that's a good point. One thing we'll be moving towards as we go, especially when we get into the next chapter, is when it comes to calculating probabilities, it's better for us to look at probabilities involving several things where we've averaged it together instead of just one trial. So based on the expected value, the long run average, we would say that this second game of craps on the pass line, is a better game to play. Okay? Okay, we got several other things here. Oh, let's look at this one about the life insurance. Very good one. It says there is a 0.9968 probability that a randomly selected 50-year-old female lives through the year. A Fidelity life insurance company charges $226 for ensuring that the female will live through the year. If she does not survive the year, the policy pays out $50,000 as a death benefit. Okay, from the perspective of the 50-year-old female. Let me tell you why it says that. You know, depending on which side of the table you're on, you're getting a loss or a gain. Okay, so we could do it from the perspective of the insurance company, you know, or we could do it from the perspective of the person that they're selling this policy to. Okay, so we're looking at it from her perspective. What are the values corresponding to the two events of surviving the year and not surviving the year? Okay, if she survives the year, what's happened with her as far as her money? She just paid out $226. So we would say surviving the year is negative $226. Okay? However, if she doesn't survive the year, then somebody gets $50,000 minus $226. So I got $49,774. And I'm not sure why I put a parenthesis there. So let's just erase that. Okay. All right, so those are the two values. Okay. If a 50-year-old female purchases the policy, what is her expected value? And so given the probabilities associated with each of these, we can say the expected value is, okay, she lives through the year, so that's negative 226 times the probability that she makes it through the year, which is what? Okay, 0.9968. Okay, plus she doesn't make it through the year. So that's when we get the payout. And the probability that she doesn't make it is going to be what? 1 minus the 0.9968, which I get 0.0032. Okay, so that's times 49774. Okay, plus 226 negative times 0.9968. I got negative 66. Is that what you all got? Okay. So if we lined up 1,050-year-old women that purchased this policy, okay, and then at the end of the year we assessed, you know, each of them is going to do one or the other. These are the outcomes. They either lose 226 or somebody gets this, okay? But when we average those things together, we would expect that the average benefit would be a loss of $66 per person, okay? Questions about that? Okay, very good. Which means, basically, that the insurance company is doing what? Making about $66 per person, okay? All right, can the insurance company expect to make a profit from such policies? We would say what? Yes. Okay, yes they can, because the customer is averaging a loss. Very good. All right, that's about all I really want to say about expected value. We may or may not have some time to talk about